Selamat pagi semuanya.
Pagi, Bu.
Kita tunggu dulu yang lain ya. Oke, selamat pagi semuanya.
Selamat pagi, Bu.
Masih tunggu kehadiran Dr. Wenda.
Hi, morning.
Hai, Dr. Wenda. Very good morning.
Let me share my slides.
Okay. I just heard some vibration of my voice. No? Can you get my voice clearly, Dr. Wenda?
Yes, I can hear very clearly.
Okay.
I'm not
Thank you
sure
so
why
much.
I got disconnected for a while. Just share this. Okay.
Okay. Yesterday, Prof. Rohana just contacted me through email. She informed about the opportunity to extend our, collaborations between UPI and USM. And then, she offered I guess this is maybe the new program or just the routine program in USM. It called, dual degree for master and PhD program.
It's like a special program whereby you can have 2 different degrees from different universities. Yeah, I think that one needs some planning to see which course is a suitable one and so on.
Yes,
I think that's a very good approach because students will get experience from different places. Right?
Yeah. She named this program as the joint degree. So for master in science for mixed chemical instrumentation or even though double or dual degree program for master and PhD by research, I guess.
Yes.
And for master program, she also mentioned that it would be offer the coursework tentatively for sustainable chemistry and management.
Oh yeah. So we actually have this kind of a program with some other universities too. Like one is in France. We have like a joint PhD program, and another one is in Japan. Yeah.
I see. I see.
So we want to extend it to collaborate with you.
Okay. Yeah, that's very great information and also great opportunity for us. And then yesterday I have reply the message from Prohana, and then just wait and see for any requirement that need to be prepared from my side to respond that program.
I think the first step will be to sign the MOU. I think we have signed, right?
Yes, that's right. That's right. Yeah. We've been drafted, and also maybe in USM side, Prohana and also Prof Melati, I guess prepared it already. Just maybe to see each other the point in the agreement. It would be not take so long time, I guess, to sign that one. Okay, so gradually the student and also the participant join with us. So very good morning, everyone. Welcome back to our lecture series here. And very, please, Dr. Wenda already joined with us again. Now we come to the week 5, today, I guess Dr. Wenda will continue the delivery of the content, for this lecture, and then for the detailed information and also the lecture content, it would be directly delivered by Dr. Wenda. So, Dr. Wenda, time and place is yours.
Okay, so thank you so much for the opportunity to give this lecture today. So I just want to start off by giving you this overview of the assessment that I'm going to conduct. And from week 1 to week 5, today is week 5. So we have several assessments, right? The first one, week 2, we have poster, and then after that, last week we have essay assignment, which will be due next week, right? So this week I have an assignment whereby I give you all questions. So these questions have to be answered and submit to me by week 7. Okay, so you have 2 weeks time to look at the questions. The questions I have already uploaded online. You can look at the Padlet website. You can have today's slides also. I have already uploaded that. So please have a look at the questions. It's related to membrane adsorption and the first week's lecture. So try to answer it. It could be a bit difficult for you to answer, but you have time to look at it and try to do some revision so that you can answer it correctly. It will be 25% of the overall score. Okay, so we want to continue from what we have left out last week. Right, so last week we talked about some fundamentals and application of adsorption. We looked at how adsorption is applied in wastewater treatment plant and what are the different types of adsorption system that we have. Right, we have the continuous system, whereby you have activated carbon column, and then we have another one is a batch system. Right, both have its own pros and cons. Right, continuous is more practical to operate, but of course you sometimes have problem with clogging and so on. And batch system, you have difficulty in recovering the adsorbent, but it's not like we want to recover it, but sometimes the adsorbent that we use it just one time and then we will need to discard it. So that depends on the application. We also look at one of the wastewater treatment plant that uses activated carbon to remove micropollutant, right? So if you look at the slide, you can see for yourself the photos of the wastewater treatment plant and how it's used, how activated carbon is used to operate it. Okay, so we also talk a bit on techniques to prepare adsorbent. I remember one of the students asked about how to increase the surface area of the adsorbent. So generally, if you are using biomass waste as your sorry, I need to switch off the. Okay. Okay. So generally, if you're using biomass waste as your precursor to prepare your activated carbon, right? By right you should activate it, right, to have higher surface area. So activation means that you want to make pores, okay? Increase the porosity of that particular activated carbon, so that you can have more surface area, and more surface area means better adsorption properties. Yeah. So to increase the pore, right, the porosity of the activated carbon, there are 2 different techniques widely used. One is the physical activation. The other one is the chemical activation. So physical activation, you use gas like carbon dioxide or steam to create pores of that carbon. On the other hand, if you use the chemical activation, you are using things like potassium hydroxide or maybe nitric acid to react with the carbon so that you can have pore formation. Okay, so all this formation of pore is very important because it gives the activated carbon higher surface area for adsorption process. Okay, so today we want to talk a bit on techniques to characterize adsorbent. I'm going to give you some example of what research has already been carried out to look at how once you prepare an activated carbon or an adsorbent, how you can characterize it and what are the importance of each characterization method. Okay. So as I mentioned last week, we have many different types of characterization method ranging from nitrogen adsorption, desorption, XRD, and so on. So we have covered some of the fundamentals of this characterization technique. For example, we will look at this thermoporometry, which relies on the use of temperature. Right? We also look at mercury porosimetry, whereby we are measuring the pressure, the volumes of mercury. Right? We use pressure to push the mercury into the pores, and we measure the volume of the mercury. And then the volume of mercury will entirely correlates to the pore volume. Right? So these two, if you are doing an adsorption study, let's say water adsorption of a pollutant in water, right? Always water. This thermoporometry and mercury porometry method, these two methods, they are less likely used. Okay? They are seldom used compared to the nitrogen adsorption desorption. So this method is more commonly used. And the reason is because most of the time when you want to characterize a pore structure, okay, the porosity of the activated carbon, it is usually in powdered form, right? So powdered or granular form. So if you are using granular powdered form, the better approach to determine the surface area, the pore volume, pore densities would be to use the nitrogen adsorption desorption, because this method is simpler and very easy to operate compared to when you want to use thermoporometry and mercury porosimetry. Okay, so that's why you can see all the papers that you have, right? You find most likely they use nitrogen adsorption desorption. Okay, so all the information or most of the information that you get for thermoporometry and mercury porosimetry, you can get it using nitrogen adsorption desorption technique. Okay, so that's why this is very widely used in all papers. And for nitrogen adsorption desorption, this one we carry out using the porosimeter. Okay, and in all adsorption paper, this result is a must. Okay, so when I review any papers, either it's adsorption or catalyst paper, the first thing that I look at in the characterization section will be the surface area. Okay, the specific, whether they explain, they give the surface area or not. If they did not give this information, then I will either ask them to give it, or if the overall quality of the paper is not so good, I will just reject it. So this is one of the most basic data that you have to have. Okay? Because if you talk about adsorption, it is a surface process, and surface process has to be characterized using the specific surface area, okay? Or using this nitrogen adsorption desorption technique. And other things like XRD. Okay, XRD, as I mentioned before, is to look at the crystal space of an adsorbent. Right? So XRD technique is a very powerful technique, okay? Especially when you want to prepare inorganic adsorbent. Because inorganic adsorbent can be many types, many different types, right? So when you are doing this adsorbent, right, you're preparing this adsorbent. Let's say you're preparing boron nitride. right? Boron nitride as your adsorbent. So once you carry out the preparation process, you will not know whether you have successfully obtained that particular adsorbent or not. You have to characterize it. So usually XRD is the best approach to characterize the adsorbent, okay, to tell you whether this one is your intended adsorbent or not. Okay, so sometimes you get something else, okay, something different. Okay, when you prepare adsorbent, sometimes you want to get boron nitride, but when after you prepare, you get something else, and that something else perform better than your originally intended adsorbent. So you have to change a bit your story. So when you're writing a paper, right, you have to change a bit of the story so that you need to shift it to the other adsorbent. Okay, this is something that usually a researcher do lah. Okay. Next one would be scanning electron microscopy and TEM. Okay, so SCM and TEM, they can be used to look at the morphology, to look at whether your adsorbent it has a porous structure or it has a non-porous structure, or maybe it has a very unique morphology, right? That can be used for adsorption process. So I don't know whether you all have seen the different types of morphology of adsorbent or not, but just to share with you. So if you look at activated carbon, right, sometimes it is just a particle. In activated carbon, you can have a particle, right? Just like that. There's no pore structure. Sorry, there's no unique morphology. Okay, there's pore structure, maybe macropore here and there, but there's no fixed morphology. It's just particle. Okay, that's activated carbon, right? So if you look at inorganic adsorbent, things is a bit different. Okay, inorganic adsorbent, sometimes let's say you have you want to develop Fe2O3, right? Fe2O3, you can also develop it to become one type of a adsorbent. Let's say you want to develop another one, FeOOH, right? This is also another one type of adsorbent. Okay, so some people instead of developing it into something like the activated carbon structure with a lot of pores, some people develop this iron oxide morphology to be something like this, very sharp, sharp structure like this, like a sea urchin, right? You know sea urchin, right? It's like rambutan, right? Rambutan structure, right? You have seen rambutan, right? Because we are in Southeast Asia, a lot of people like to buy rambutan. So we can actually develop the materials to become this kind of structure, like a rambutan shape. Or if you do want to become rambutan, you can make it into something that is very unique. Maybe like a plate structure with a lot of pores, right? Or maybe like a star structure, right? All these, they are doable. But the better one would be, I would say, something like a sea urchin, because it gives you more surface area. So in fact, there are researchers who do this kind of study and develop this kind of catalyst. And most of the time, to get very unique morphology, you have to use a hydrothermal method. Okay, so hydrothermal method is one of the techniques whereby you are using pressure and temperature to control the growth of the crystal, right, or the adsorbent, right? So when you control it using this heat and pressure at certain condition, you will get something that is very unique with high surface area, and you can use that for your adsorption process. So this FeOH and Fe2O3, people, the researcher using it for arsenic removal. Okay? They are very effective in removing arsenic, okay, iron oxide. But activated carbon is not so because of the surface groups. Okay, sometimes you have to know why everyone different people prepare different kind of adsorbent. And the reason is simple because not all adsorbent can be used to absorb everything. So you have to selectively look at the type of pollutant that you have in the wastewater. If you have arsenic and you want to use activated carbon to remove arsenic, it's not going to be effective. Okay? The adsorption capacity will be very, very low compared to when you use iron oxide as your adsorbent to remove the arsenic. Okay, so that's why we need to have SEM and TEM technique to look at the morphology, okay, of the adsorbent. Besides morphology, we can also look at the distribution. Okay, elemental distribution of the adsorbent. Okay, let's say you have activated carbon and you take it from rice husk, right? So rice husk contains a lot of silicon, right? Si. So when you look at the mapping, you'll see that you have Si all over the place. Okay, so this is something that can tell you whether your adsorbent contains what inside. Okay, and it can also tell you whether there's any possible contamination that could happen if you choose this as the adsorbent. Okay, for example, if you are using sludge, okay, activated sludge, when you go to secondary treatment, you will use microorganism to remove your pollutant. So this microorganism, right, they are sludge, they grow excessively, and if you collect the real sludge in wastewater treatment plant, they contains a lot of heavy metals. So if you take this sludge as your precursor to prepare your activated carbon, right? So you'll get that you'll get activated carbon, but you also get a lot of sludge, heavy metal. Okay, in the sludge, you will also have a lot of heavy metal. Okay, and all these heavy metals, they are not stable, which means that they can leach out from the activated carbon. So through the EDX, using SEM, right, you can actually look at the distribution of that metal, and you can quantify it, okay, so that you know, okay, this one is not suitable for application in water. Okay. Okay, other things like XPS. Okay, XPS. You can look at the chemical configuration. Let's say you have carbon, right, been attached to something. Let's say phenol. Okay, carbon and phenol. There's an interaction between these two. Okay. So you can take the XPS data, the reading, before and after, so that you can determine what functional groups has already been shielded, right? Sometimes when you have this interaction, you want to detect the functional group using XPS, you cannot detect. Okay, which means that before adsorption and after adsorption, you have XPS data. So before adsorption, you can see there's one peak, one additional peak. Compared to after adsorption, that peak disappears. Then you can deduce that this peak, okay, is the one that is the active site for adsorption process. So I'm going to give you an example later of how this can be done. Okay. So other things like NMR is mostly for the inorganic catalyst. Most likely people will not use this NMR for activated carbon. Okay, sometimes we use NMR to look at the characteristics of the inorganic adsorbent like zeolite, okay, and maybe like something that contains certain species that can be detected with NMR. Okay, it's not just limited to proton, but sometimes people look at the phosphorus NMR, aluminum NMR, and so on. So there are many types of NMR. So another characterization AFM, but AFM we don't really see it a lot if you are looking into applying GAC or PAC. Okay, if you prepare granular activated carbon, powder activated carbon, probably AFM will not be very useful. Okay, besides all these instruments that you use to characterize your activated carbon, we also have different techniques okay, to look at the porous structure, okay, porous structure of the materials. For example, adsorption capacity. Okay, some manufacturer, they will give you adsorption capacity of a certain pollutant or maybe a certain chemical, to show you that what is to benchmark against other activated carbon, and to show you whether this particular activated carbon that they have is useful for that application or not. Okay. Some people, some manufacturer, they use iodine number. Okay, so this iodine number is one of the most common parameter used for characterizing porous material. So iodine itself is a very small molecule, a small small atom. Okay, it's a small ions. Okay, so we look at the adsorption of this iodine by the activated carbon, and then we can roughly compare between different types of this activated carbon. So usually it's around 600 to 1,200, I think, the range and the adsorption capacity, okay, the iodine number. Okay, and it's measured through the adsorption of iodine on activated carbon, okay, at the fixed solution of iodine. Okay. So we also have this something called a phenol number, which means look at the adsorption of phenol on the activated carbon. Okay, the standard phenol solution, you carry out adsorption process, right? Then you can see how much phenol has been adsorbed. Okay, and besides phenol adsorption, we also have phenol desorption. Okay, as a way to characterize phenol adsorption and desorption process. Okay, and from here we can look at a lot of things in terms of the porosity, the pore volume, and so on. Okay, and pore size. And last one is the molasses number, the more common one. This one is look at the characterization based on the removal of color. Okay, you have a standard solution, and then this standard solution, you use activated carbon to carry out the colorization. Okay, so there are many ways where molasses number can be conducted, okay? And there are many things that influence this this result. For example, pH, you have temperature, and so on. So if you want to compare, let's say you have two manufacturers, they give you this molasses number, they give you different number, right? And you want to compare them. It is not really possible unless you know that the condition that they use to conduct this study is the same. Okay, because usually different manufacturers, they have different ways of conducting things. So sometimes pH can be different, so the results can also be different. Okay, so you have to be aware of this when you want to compare across different manufacturer and different activated carbon. Okay, so this one means the color ability to decolorize, usually 90% with 90% efficiency. For some manufacturer, they prepare a standard solution, right? Let's say a standard, let's say one ppm, right? Then they determine the amount of activated carbon needed to decolorize 90% of that 1 ppm. So that would be the number that they report. Sometimes they do that. Okay? This means that the lower dosage that they report, the better it is the adsorption process, okay? The adsorption capacity. So all these are the basic characterization, okay, that you will find in all these four, okay, these four you will find in the information given to you by manufacturer. Okay, but there are less common when you are looking into papers describing adsorption of the pollutant. Right, you will not see this very often. Okay, in the scientific publication. Okay, but they exist okay, they are there. Okay, so I want to share with you how adsorption study can be conducted. So I'm aware that some of the students are doing adsorption experiment. So I just want to share some ideas and what are the things to look out for, so that when you are doing your adsorption study, you probably can improve. If you still have time, you can think of some innovative way, and eventually, hopefully, you can get these results that you have and publish it out. Because as we all know, for our project for research project, okay, it is not good enough. We only get an A, because as a researcher, we don't want just to get an A for our project and that's it, right? We want to move up one level higher. We want to get these results, and we want to publish it out, right? So when we publish it, then people can read about our work, and then we can be proud of ourselves. We can also be happy that we contributed something to the scientific world, right? So for this this one, this paper, okay, this is one of the research work that I did in 2019. We look into developing boron nitride as an adsorbent. Okay, so reason why we want to choose boron nitride is because at that point of time it is quite popular. Okay, and if you look at the literature, boron nitride, right, you can find that there are almost 1,000 articles on boron nitride, but not all of adsorption, because adsorption using boron nitride would be like maybe less than 50. Okay, so there are people reporting boron nitride as an efficient adsorbent. Right? So at that time, this research is conducted by one of my FYP students. Okay, and we managed to publish it out. Okay, and we try to develop this boron nitride. Okay, and we want to test it out for heavy metal adsorption. So our strategy is to look into how we can prepare the boron nitride at different temperature. Okay, so we vary the temperature for this adsorbent preparation, okay, from 750 to 1050. Okay, so we use 3 different temperatures to prepare. 750, 900, and 1050. Okay, and then after that we study the characteristics of the adsorbent, okay, to see when we vary the temperature, what can we get. Okay, so if you are looking into working in adsorption area, the important thing that you have to take note is that if you are just preparing an adsorbent using one condition and then characterize it, that will not work anymore. Okay, if you want to publish it, right? So now we want a lot of people are looking into fundamental side. Okay, we want to look at when you want to prepare how a certain parameter can affect the preparation process. Okay, this is something that has to be incorporated in the paper. Okay, for this case, we look into temperature, how varying the temperature can affect the characteristics of the adsorbent. Okay, we want to look at that. Of course, if we can prepare directly one boron nitride at one temperature and just use it like this and do the routine study like fitting it using Langmuir isotherm or Friedrich isotherm and so on. But that will not be so interesting for the readers. Okay, so for this case, the first thing that we did, okay, after we vary the temperature, okay, from 750 to 1050, is to look at the XRD. So reason why we need the XRD is because, as I said, this is an inorganic adsorbent. And for an inorganic adsorbent, XRD is very important because it tells us whether we have successfully developed the adsorbent or not. So if you look at the XRD for 750 to 1050, right? How can I tell I have successfully prepared this boron nitride? Very simple. I compare it with the library, right? So once I get this XRD pattern, I compare it with the library, and I will have, if I have boron nitride, I will have two different peaks at 002 and 100. Okay, so you can see here for this 1050 boron nitride, we have these two peaks, which means that at 1050 I have boron nitride. Okay, I've successfully prepared this. If I vary it to 900, okay, I change the temperature to 900, I also will have these two peaks, this peak and this peak, right? If it's 750, same thing, I will have this one and this peak. But the only difference between these three is that for 750, right, I have additional peaks coming up. Okay, so this shows that indeed I successfully developed boron nitride, but if I have lower temperature, 750, the boron nitride has certain impurities. Okay, so this is how we look at the XRD data when we characterize it. XRD, these are the information that we can get. Okay, whether it is a pure boron nitride for this case, or it is a mixture of something else. Okay, so what is this something else? Okay, what is this something else? It could be boron oxide. Okay, it can be anything. Okay? So we have to match it with the library to tell. Okay, so now that I know different temperature, will eventually also get me to fabricate this boron nitride. I can get it. Okay, I can get this boron nitride. Next step, I look into the surface functional groups using FTIR. So this technique, FTIR, I use ATR method. Okay, we use ATR method. ATR FTIR means that there's this configuration in the FTIR whereby you don't have to prepare the KBR palette. Okay, so when you are doing FTIR for solids, you have to use KBR, right? Most of the time you have to use KBR, right? Potassium bromide. You mix potassium bromide with the adsorbent, and then you prepare the pellet, right? So this pellet, you use it and you use it to analyze for the FTIR, okay, the adsorbents. So the reason why we choose KBR is very obvious, because KBR will not give you any peaks in the FTIR, the IR region. Okay, that's why we use the KBR. So some some of the students ask me, I received these questions here when I teach their course. They ask me whether they can use any ACL or maybe something else to replace KBR. So generally the answer is no, because some of the salt may give you IR signal. Okay? That's why we choose KBR, because it's transparent to IR. Okay? So from this FTIR, you can get those peaks, all the peaks, okay, the characteristic peaks that you have. Like for example, the OH group, this part will always give you the OH group and some amine group and so on. Okay, so this one also, once you get the peak, you have to compare with the library. Okay, the library will be able to tell you what kind of peak you have. Of course, you have to compare it intelligently. Okay, let's say you have a peak at this region, right? This region 1600 and below, maybe 1000 and below lah. Okay, 1000 and below. Usually we call it as the fingerprint region. Okay? So which means that it's unique to a certain adsorbent, right? So when you are comparing, okay, the FTIR, and you must compare intelligently in terms of the peak that you want to assign to. Okay, example, let's say you know that at 1000 FeO will give you this signal, right? Like iron and oxide, okay? They have this signal at around 1000 to 900, around that range, here, this range. Okay, so you have to compare in a way that, okay, for my adsorbent, I don't have any iron, so I cannot assign this particular region to the iron. Okay, you have to compare intelligently. You have to know what things that you have in your adsorbent before you can assign the group. Okay, so if you have only boron and nitrogen, then you assign based on boron and nitrogen. Okay. So next one, this one, SEM and EDX. I looked into the morphology of the adsorbent. So you can see clearly this is the adsorbent that we have, and there's no pores. Okay, the pores are not so obvious here. So there's no macropore. It's just like a particle-like structure. Okay, but the good thing is that when we carry out this EDX mapping, okay, you can also do something like this EDX mapping, and EDX will tell you about the distribution of the elements. Like boron, you can see boron distribution is here, like all this part. So all this is your boron, and then the nitrogen also here. Okay, they are centered around the same part of the SEM image, right? This part. Right? So we can look at it and we can say that the boron and nitrogen, they are distributed homogeneously or evenly. Okay? So if you have like a two-phase, okay, let's say you're preparing a composite structure, and the composite structure contains more than one type of material, right? So let's say you have you want to prepare Fe2O3 and PaO2 as your adsorbent. Okay, some people do prepare this as their adsorbent, and you look at the SEM and EDX data. Okay, so the good one, okay, the good approach, okay, optimized approach of preparing will give you maybe like a, let's say your TiO2 is a support, right? Then you have a lot of Fe2O3 attached to it, right? So this will be the ideal nano composite. Okay, this one we call it as a nano composite. Okay, the ideal one will be these two together attached, right? So if you look at the EDX mapping, you will see that this region attached to TiO2 will be Fe, and then this whole thing will be the Ti. Okay, and if you don't optimize the synthesis, okay, let's say you just simply prepare it at the non-optimized ratio between Fe and Ti, you will get a mixture. Okay, definitely you have a mixture, which means you have Fe, Ti, Fe all over the place. Okay, maybe some Fe attached to the Ti also. Right. So a mixture itself means that the synthesis has failed. Okay, you cannot get the nano composite that you want. Okay, so this information, whether you have a mixture or you have a nano composite, if you look at these three characterization method, A, B, and C, right? The only way you can really tell very certainly is you conduct SEM and EDX study. Okay, then you know that you have a mixture. Okay, if you only look at the XRD, right, you probably will not be able to tell that you have a mixture. Okay, unless you do refinement of the XRD. Okay, and then maybe to some extent you can tell that you have a mixture. Okay, but the information that you get that will reveal that you have a mixture and your synthesis fail is the SEM. Okay, so that's why we need to do certain all this characterization so that we know that we have successfully developed adsorbent. Okay. So another characterization. Yeah, look at is the XPS. Okay. So XPS tells me about how boron and nitrogen behave. Okay, what are the bonding configuration that I have in the adsorbent. So you can see here when I carry out the survey, this is a survey scan. Okay, survey scan, and whereas this one is the other one is the high resolution scan. Okay. Survey scan means that I'm scanning everything. Okay. And from scanning everything, I get to see that my adsorbent consists of boron, nitrogen, and oxygen. Okay, 3 different things. So of course, if you only look at the previous one, yeah, this one, all this characterization, okay, I don't see any oxygen, right? So I will exclude oxygen, right? But from the XPS result, it gives me oxygen. So this means that I have oxygen. So without doing XPS, I will not be able to tell that I have oxygen in the boron nitride. And oxygen presence in organic material, they are quite common. Okay, sometimes let's say you have, this is your adsorbent, sometimes you have surface hydroxyl group, surface OH group, right? So all these, they are very common, especially for the basic materials, okay, like magnesium oxide, and so on. So all these, they have the surface hydroxyl group. Okay, and surface hydroxyl group is important because it can affect the characteristics of that particular materials. Okay, so sometimes more hydroxyl group, it's more hydrophilic and so on. Okay, so from here I can also tell, okay, from the high resolution image spectra, okay, high resolution spectra, I can also tell that oxygen is bonded to this boron, and I also have oxygen bonded to the nitrogen, right? So I can deduce all this from the XPS. Okay, so XPS, to run this XPS, is quite straightforward, very simple to get XPS. Unlike TEM is more difficult to operate. Okay, so let's say you have let's start with SEM first. So if you have SEM and you have adsorbent, right? You want to look at the SEM image using and with the adsorbent sample, okay, using a powdered sample. So what you need to do is there's a sample holder in the SEM. It looks like this, something like this. You can stick carbon tape, right, on the sample holder, right, and then after that you can put a bit of the powder, okay, the adsorbent on the carbon tape, maybe just a drop just a tiny drop, very small drop. Okay, you cannot put a lot of sample. You have to put just a bit of sample, because if you have a lot of samples on the carbon tape, right? Let's say this is the carbon tape. You put a lot of sample, okay, excessive sample. So when you do the imaging, right, you will see a lot of charging effect. Okay, when you have charging effect, that means uh, your image will have a lot of bright spots, which makes this image not usable. Okay, you want to use it for publication, it's not going to work. Okay, the editor look at your image and he will just reject the paper straight away. So that's why we cannot put a lot. We have to put just a bit, just a tiny small amount, maybe a drop. Okay, so while this small drop, right, the small drop looks like it's too little for you, but when you zoom it using the SEM, you will see that this is actually a lot, right? A lot of samples, right? So once you have put this sample on the carbon tape, you take the whole sample holder and put it into the SEM, okay, and then you remove all the air inside. Then you can switch on the electron beam. Okay, there's an electron gun here. There, okay, it depends on the SEM that you have. What are the source of the electron? Right. So then you can do some imaging now. Whether you want to use the backscattered mode or you want to use the secondary electron mode. So most of the time we will use a mixture of both. Okay, a mixture of both will give you a better image. So some backscattered and some secondary electron. You can control it. In certain SEM, you can do this adjustment. Okay, so then you have to adjust certain things. Okay. Once you switch on the electron gun, the beam will hit the electron, and backscattered electron, secondary electron comes out. Then you need to adjust the focus and the something called the wobbling, okay, so that the image will be clear and nice. Okay, so that's for SEM. But for TEM, things will be a bit more challenging to operate. Okay, it's very difficult to insert a sample into the TEM, especially the higher kV one, especially a 200 kV one. Right, 200. You have 200 kV, which means it gives you higher resolution. Right. Another one is the 120 kV one. These two I operated before. Right, the 120 one is very simple to do. First thing is you have to have a copper grid, a small copper grid, right? This one you can purchase anywhere, and then you have to prepare a sample. You have to take your maybe like a tube, okay? It's like an Eppendorf tube. You take one tiny drop, okay, tiny amount of sample, like the one that you have for your SEM. You put it inside this tube, and then you add in ethanol. Okay, this is how I prepare. Okay. You add in ethanol into the tube, okay, and then you put it in a sonicator to disperse the small dot that you have. Okay, so all these small dot, the adsorbent will disperse in the ethanol solution, and you take one drop of this solution, you drip it on the copper grid. Okay, so this copper grid contains it's copper and it has a lot of grid. Okay, here all these grid, they are made of carbon. Okay, but the entire structure, the framework is made of copper. Okay, and you have a lot of this carbon inside, and you drop this sample and wait for it to dry. So once you have this copper grid been dried off, right? Then you take this copper grid, you put on the sample holder. EM sample holder, it looks like this. Okay. Yeah, something like this. Okay. So this is where you put your sample. Okay. And this is where you hold it. Okay. So here you take the copper grid, you put it here. Okay. If you can see the screen. You put it on the sample holder and then you insert it into the TEM. So when you insert it into the TEM, you have to be very careful. Right? So TEM is like this, right? And then there's a hole here. Yeah, and then the electron gun is here. You will shoot electron from up to down, and this is where you put in your sample holder. So the alignment that the way you put in is important, because once you tilt the sample holder a bit, air will get into the system, right? When you have air rushing into the system, right, then you have problem. The whole TM will shut down, right? It will shut down, and you need about a few hours to restart the whole thing again. So every time when I'm doing PM, I am a bit scared, because if I do this kind of mistake and the air rush into the system, then the next person will have problem. He will not be able to operate the PM. Then the PM will be down for like a few hours. So the person will not be very happy, and yeah, things will not go very well. Okay, so that's the things that I can share with you in terms of how we can prepare the sample for the EM. Okay, prepare the adsorbent. In terms of sample treatment of the adsorbent before you put it for TEM or SEM, usually for TEM no treatment is needed. But by right, there's no treatment, there's no special things that you have to do, because adsorbent itself, it is it is not going to be like a disintegrate or anything that easily, especially when you are dealing with inorganic adsorbent. Okay? But of course, biological sample microorganism, you want to use TEM, you have to be careful. You have to prepare that differently. But if it's just adsorbent, then you can do like what I said just now. Just drip it on the copper grid, and you can get the results. Okay? For SEM, also no specific treatment except coating. Okay, coating with a platinum or gold, so that you make it more conductive. So another one is the XPS. So when I had a chance to operate XPS previously, but for operation of XPS, you need to get for all operation you need to get license. Depends on the country that you are in. Okay, I operate all this in Singapore, so you need to have an X-ray license. Okay, you need to get approval from the government. Okay, and the university, operate anything that is related to high energy beam. Okay, so they consider this as a high energy. So for XPS, it's also relatively straightforward. You take the sample. There's a sample holder, right? Your adsorbent, you can just place it on the sample holder, and you put it into the instrument, and you pump up all the air. Okay, and you set. Okay, you set the location of the analysis that you want, and then it will be automatically operated. Okay, it will detect where is your sample, and then it will get you the results. So now it's more like the automated system. Okay, whereby you don't have to manually do one by one. Okay, you can put 10 sample into the sample holder, and it can run all the results. Okay, just that running it is simple, but interpretation is difficult. Okay? So if you run the high resolution one, the things that you will get is something like this. Just two different overlapping curve. So from the overlapping data, you have to carry out deconvolution, okay, to separate the peaks using a software. And after separating the peaks, you have to look at what is the binding energy. Okay, this binding energy. And from the binding energy itself, you can assign it to something. Okay, this one you have to compare it with the literature or with the standard library, okay, to see what peaks are there. But sometimes when you are doing something that is very novel or unique, then that's a problem, because you have to really know the sample well. Okay, you have to confirm it using other methods, because there's no library or there's no literature for you to compare. Okay, so it is not so simple. The XPS is one of the toughest instrument, okay, to analyze and to interpret. Okay. Okay, so the next one that I want to share with you all is this one. This is another article that we managed to publish this year, and very much related to the conversion of biomass waste into carbon. Okay, for this case, we are looking into biochar. Okay, nitrogen doped biochar, which means we dope the biochar with nitrogen compound. Okay? And this I show this because it is quite related to the adsorption study. So for this study, we use it for different application, but it is related in terms of the characterization technique that I use. So for characterization, we did several things like from XRG, SEM, EDX, and so on. Okay, we also looked at the Boehm titration, Raman, and CHNS. So all these are very common characterization techniques that you will see in and you probably will need when you are doing adsorption experiment. Okay, so why I did all this characterization? First one is that in terms of XRD, we use this technique, and we look into the carbon phase that we have. Okay, so before that, for this conversion of wood residue or sawdust, okay, we use sawdust as our biomass precursor, okay, or bio waste, and we add in different amount of urea. So we mix this thing, the sawdust, with urea, okay, because urea is a good nitrogen source. Okay, we mix it, and then we carry out pyrolysis to get the materials that we want. Okay, and we vary the amount of urea from 5 gram, 10 gram, and 20 gram. So we look at the XRD. So XRD itself, yeah, you can see for yourself here. This XRD shows the presence of 2 peaks, right? And then when we look at the library, we try to match it. We found that what we have is amorphous carbon. Okay, so this is very likely what you will see in almost all activated carbon. Okay, or most of the activated carbon will consist of amorphous carbon structure. So you will have 002 and 101 here. Okay, these 2 peaks, right? So, and another one thing that you can look at to confirm that you have amorphous phase is that you look at the background. So the background is like this, right? It's not really straight. It's like moving down, something like this. It's going down, slanted. Okay? So this means that you have amorphous compound, okay? Which means that the background is quite high in terms of the noise. Okay, so it's amorphous. So if it's crystalline, then you will get very sharp peaks. Okay, sharp peaks means crystalline, but of course, sometimes you have crystalline materials, but it gives you like not so sharp also, right? But the background is not like this. Okay, the background is not like going down. It is straight, but it is not so sharp. This one has to do with the size of the adsorbent that you have, okay, of the material that you have. If the size is nano size, then sometimes you can have this kind of effect. Okay, the crystal packing is not like, it's not under pressure. This is what I can say. It's not under pressure, so so you will have this to some extent a broad peak. Okay, but the background must not be like going down. Okay, if it's going down, then it's amorphous. Okay, so this is how we interpret the XRD data. So for this case, it is amorphous carbon. Then we look at the Raman characterization. So for carbon, sometimes we like to look at the Raman because we want to know the surface defects. Okay? Surface defects means that, okay, let's say you have the graphene as your adsorbent, right? So this graphene can be arranged together. Okay, it can be a perfect graphene, okay? Or sometimes this graphene could have defects, which means that some of the arrangement, they are not 100% arranged together, as in, okay, not exactly what I'm trying to say. It's something like this. It's arranged like this, right? So if you have defects, maybe you have, let's say, this one ring, okay, and then the other one you have something that is not really bonded with this one. Okay? Originally you intend it to be bonded with this one, right? Have a perfect structure, but sometimes some sites may not join with this. Okay? You have a lot of this structure together, right? So some of it could be like broken. Okay, some of the bond is not really joined with the adjacent carbon. Okay, so all these, they are the defects. Okay, defective sites. Okay, so for Raman, we can use this to study the defects. So we look at the intensity of D and G band, and from the intensity we can tell, okay, whether you have a defective structure or you have you have a perfect non-defective structure. So you can compare between them. Okay, so we also look at CHNS. CHNS is for us to look into the amount of nitrogen. Okay, so since we're doing nitrogen doping, we look at the nitrogen content. And if you use 5 grams, you have 8 weight over weight. Okay, 8% nitrogen weight over weight. 10 grams, you have 8.2, slightly increased, but you have 20 grams, you have 12. Okay, so it increased a lot. So yeah, in the specific surface area, we use this porosimeter, and we found that it's quite high. You know, the specific surface area is up to 900 something. Okay. Boehm titration. This one is easily done to determine the surface acidity. Okay, surface acidity means that whether you have any acidic functional group or not. So total acidity, this one I titrate it with NaOH. Okay. So generally, how this is carried out is that you have your adsorbent, right? And then you add, let's say you add sodium hydroxide. Okay. You know this sodium hydroxide, what's the quantity of sodium hydroxide you have, you add to the adsorbent, okay? And then you shake it for 2 days, 1 day or 2 days. Okay. So after 2 days, you determine the amount of NaOH left in the solution. Okay. So this means that the remaining NaOH, the rest, the one that disappeared, is the one that has reacted with your adsorbent. Okay. So from there, you can determine what is the total acidity of the adsorbent. Okay. And you also can look into carboxylic group, lactonic group, and phenolic group. So all this, you have to change your base. Okay. For total acidity, we use sodium hydroxide. For carboxylic acid, lactonic group, or phenolic group, we use something else, maybe like sodium carbonate, okay, and so on. So we use something else with a different strength, okay, different basicity. Okay. So NaOH, you know, is a very strong base. That's why we use it to neutralize all the acidic group on the adsorbent. So you can choose other things, and from there you can deduce what are the amount of lactonic group that you have, what are the amount of phenolic group that you have, and so on. Okay. So XPS, as I said, looking into the bonding configuration, right? So once you have the nitrogen group, you know that you have the percentage of nitrogen up to 12.1. If you only use CHNS, you only know up to that point. So to bring it one level higher, we take this XPS, right? And then we carry out the high resolution XPS study to look at the nitrogen site. Yeah, all these, they are nitrogen, okay, for nitrogen. And from the nitrogen XPS spectra, we can see something like this, this peak. And then we do some deconvolution, okay, using a software, and we find out that it can come from 3 peaks. So this peak 1, peak 2, and peak 3, right? So we can assign peak 1, let's say one is pyridinic nitrogen. The second one is pyrrolic nitrogen, and the third one is graphitic nitrogen. So we can actually look at the nitrogen and we can tell what type of species that they have in the activated carbon that we prepare. Okay. This is significant because some of these species may play a role in adsorption process. Okay, so before adsorption, you have this 3 group at 23, 43, and 32%. So after adsorption, if your pyrrolic nitrogen group disappear, okay, then you can match all these things together. You can correlate this, and then you can deduce that the pyrrolic nitrogen is the one that is the active sites for your adsorption process. Okay. Other things, again, just to quickly go through this, SEM, look at the pores. You can see the pores, right? the pore structure. And then EDX, okay? EDX sometimes can tell us the difference between two different adsorbent that we have. Without nitrogen doping, there's nothing here, right? No nitrogen. With nitrogen, you can start to see a lot of different things. Okay, and this is how we use the EDX to compare to several catalysts. Okay. Then porosimeter in terms of this nitrogen adsorption desorption. Okay, what we have is we compare the one with without adding nitrogen and with nitrogen. Okay, so what you see is a difference in the characteristics of the isotherm. Okay, all this we call it as isotherm, and this isotherm can reveal a lot of information. Okay, first thing is that the shape of the isotherm itself can tell us whether we have which one have more micropores. Okay, looking at these two, right? These two isotherm, I straight away can tell you that C800, this one, without nitrogen, has more micropores. So how can I tell? Is from this part. Okay. For this kind of isotherm, right? If you have initial very fast rapid adsorption process below around 0.15, okay, below 0.15, that one most likely correspond to the micropores, okay, within the smallest pore. Okay. And because C800 gives me a higher adsorption volume, then I can straight away tell you that C800 contains a lot of micropores compared to the NC800. Okay. The next thing is that we look at this part. Okay, this part, this part. There's a hole here, right? So what we usually have is that when you carry out this kind of isotherm, you have adsorption process, and then the machine will go back and then have another desorption process. Okay, so that's why you can see adsorption, one line, and then the other one is the desorption process. Okay, you have to, and when there's a gap between adsorption and desorption, okay, the one is due to capillary condensation, well, which means that materials contains mesopores. Okay, it can tell you about whether it has mesopores or not. So from this, right, from the shape, okay, it has this this gap, right? And besides this gap that tells us whether it's mesopore or not, you can also know what type of pores you have in the system, okay, by looking at the hysteresis loop. This is what we call hysteresis loop. Okay, and looking at it, we can tell whether it is your pores, whether it has a ink bottle pores, which means that whether your pores is like this, okay, or maybe your pores is cylindrical, or any types of pores, right? You can tell using this isotherm. Okay, very interesting, okay, especially for adsorption process. All these will affect the adsorption. Okay, when you have ink bottle pores, right, something like this, right, then you probably will have good adsorption, right? Then all the adsorbate will be here, right? But when you want to carry out the desorption process, that will be a problem because all these adsorbed species, it has to go out from the same small hole here, right? So desorption will be a lot slower. Okay, so all this will tell you a lot on the adsorption phenomena. Right? So TGA, we look at the thermal, stability, right? So whether it is thermally stable or not, you can tell. Okay, so why is it important that we look at TGA? There are several reasons. Okay, so, last time when I work on an absorption article, I remember someone asked me about TGA. They said, okay, for your absorption process and everything that you carry out in this particular paper, all these they are carried out in room temperature. So what's the reason why you want to present your TGA data, right? So when you want to write a paper or article for publication, you have to make sure that your characterization techniques are important for what you are doing. So for adsorption process, surface area is important, SEM important, and so on. But TGA itself, you look at the difference in the effect of temperature, okay? And the reviewer asks, okay, why is it so important? So what I answer is that it's important because activated carbon that you have, right, after adsorption, the next step would be regeneration. And one of the most common regeneration is to regenerate using thermal process, okay, which means that you use heat to regenerate the activated carbon. So when we conduct this TGA study, we are actually testing the stability of the adsorbent towards different temperature, right? If the temperature study shows you that your adsorbent is not stable after 200 degrees Celsius, this will imply that your adsorbent cannot be used for thermal regeneration. Okay. So that's how I reply to the reviewer, to tell him that for adsorption, TGA is also quite important. The characteristics of this can tell us a lot of things. Okay. So from this data itself, you can see sawdust. Sawdust, right, after being exposed to about 300 degrees Celsius, everything starts to crumble. Okay, it starts to go down very rapidly, which means that the weight loss is significant compared to after you carry out treatment. Yeah, especially with nitrogen, you can have a better. Yeah, you can see here, right, it has a better stability, thermal stability, which means nitrogen doping improves the stability. Okay, so FTIR, you can see here, for FTIR, I look into functional group. Functional group important because functional groups are the ones that will bind with your adsorbent. Okay. So quickly go through this another one. This one I want to show because this study also used TEM. Okay. This one is not from my group. This one is an article published in Chemical Engineering Journal, and it is working on biochar, okay, as a adsorbent for phenol adsorption. Okay, so you can see very routine characterization. Like this one is your nitrogen adsorption isotherm. Okay, and then you also have XPS, right, and so on. Okay, and Raman. Okay, this is the Raman. Okay, so you can see one of the like I said, one of the important thing is that when you want to write an adsorption paper for publication, you will not see in higher impact factor journal, you will not see that only one, let's say N2 adsorption is only one curve is presented. You will see a lot. This sometimes when you have a lot of data, right, some of the data is not so usable. So your main data is the important one, and the side data, they are just something that you do to get the main one. So it's good to present all the data together, plot everything together in a graph to show it to the reviewer. Okay, so the reason why we want to do this, okay, the reason why we want to make the graph looks like you have a lot of data is because we want to give the impression to the reviewer and editor that we actually did a lot of work, okay, to get the data for this study. And this is very crucial, that the kind of complexity that we present in our figure will reflect the amount of work that we put into the study. Okay, so in some cases whereby we have, I received paper with one figure with only one characterization data, or very simple figure, that would be like a sign to show that the author have not really do a lot of work on that study. Okay, so it's good when you want to present a figure, you present it with the correct amount of complexity. Okay, you cannot overdo it. Okay? You cannot present the figure and make it very, very complicated until reviewer look at it, they don't understand. But you cannot present it too simple until it reflects badly on yourself. Okay, they have to be optimum. This is one of the skills that is quite important to learn. Okay. Yeah, this is what I want to talk about in terms of using as TEM. Okay, so TEM for me, using carbon as your adsorbent, and you want to look at the TEM. For me, it's not so crucial, okay. But some people did it. Okay, some researcher, and it's not like it will not review. It's not like it's not useful. It will be used to. It can be used to review certain information. For example, this one you can look at the stacking, okay? Multi-layer stacking of different carbon layers. Okay, you can see here. Yeah, you can look at the stacking and you can deduce that the adsorbent that you have, whether it is a single layer or multi-layer, it has certain significance, especially for graphene. Okay, graphene, we want to exfoliate it so that we can have a single layer, okay, as smaller layer as possible. Okay, so that you have better surface for your application. Okay, so some other characterization from the same researcher on the TGA and so on. Okay. Okay, so next one, I want to share with you certain things that are quite important to conduct the adsorption study. Okay, so these things that I think that's when you want to look at the publication, right? These are the information that most of the current reviewer and editor would like to see. Okay, just to before that, to conduct adsorption study, right? We can see a lot of people in the 2005 to 2015. What they did was they prepare adsorbent from different sources. Okay, maybe today they take orange peel, tomorrow they take palm oil. The thing, what is that called already? The palm oil, the outer layer. Okay, the thing. Okay, then some people take sawdust, some people take anything, and then they convert it into adsorbent and they carry out adsorption process, and they keep saying that okay, this one can be used for adsorption, this precursor can be used for adsorption, and so on. And then in terms of interpretation of data, they use Langmuir, Friedrich, and so on. So all this no longer able to get you to publish. Okay, so all this study, they are considered as a fairly routine study. Okay, that has become quite quite not novel. Okay, so for today, by today's standard, the standard required for adsorption study to be published in higher impact factor journal is very, very different, okay, compared to 10 years ago. So these are some of the things that the editors and reviewers are look at. This is from myself, my point of view, and from what I see in the recent trend of research. Okay, so the very crucial thing is to that will get you to publish in better journals is I can see that theoretical study has become more and more important, okay? Which means that using computational approach such as density functional theory, DFT, okay, to model the adsorption process, okay, to look at which of these functional groups is likely to be the one that control the overall rate of reaction. We can also use the computational approach to model what functional groups attach to the adsorption site and so on. So theoretical study has improved over the years. It has already become like something very, very important, okay, in every papers, absorption papers and catalysis paper. Okay, incorporating computational study will make the overall article more interesting to look at. But of course, to do computational study, you have to have the software. Okay, some people use Gaussian. Okay, Gaussian is one of the software where you can use it to carry out DFT. Okay. Others, I'm not aware of others that is user friendly. Okay, so most of the software, yeah, quite difficult to use. Okay, and at least you need to do some coding, coding to build the molecule. Okay, to build the adsorbent interface and then to look at the interactions and so on. Okay, so it is like quite challenging, but you can explore this if you have the time. Okay. Next one is to look into controlling the functional groups, okay, on the adsorbent surface. So if you use biomass, right, as your precursor, so the biomass itself it has a lot of functional group. So if you can find a way to control that functional groups, okay, maybe to make it all carboxylic group, okay, or maybe to make it into 50% carboxylic, 50% phenolic group, then that is a very novel work. Okay. Besides that, there are people also looking into mechanism of adsorption, okay, how a pollutant can interact with the adsorbent using instruments. Okay. Like let's say you have heavy metal adsorption process, right? So heavy metal adsorb on the inorganic adsorbent. So you can use XPS to review how this process works. This is something that is of interest. Mechanism is always important. Okay? Then developing a new mathematical model, okay, like adsorption isotherm kinetics or transport model. So all these adsorption isotherm, like when we look at the adsorption isotherm, we always think of Langmuir and Friedrich. Okay? I also shared with you last week that we have a SIPS isotherm, you have the Reddish-Peterson, you have all these kind of isotherm. In fact, you have I believe you have more than 100. Okay? Many different types of isotherm. So some of the reason why researchers come up with different types of isotherm is because sometimes they want something that is novel, right? Novel and never heard before. As long as your isotherm, the one that you develop, is scientifically sound, which means that you can use it for certain condition. You can develop that model. You can use your name as the isotherm. Okay? Like Langmuir, he used Langmuir as his isotherm. You can do that also and publish the paper. Okay, so whether the scientific community accept that model as the main model or not is another story. Okay? The main thing is that you have this model, you develop it yourself, and you publish it. And it's more likely to publish if you develop it yourself. Okay, that's something new. Okay. And others like the mechanism of formation of adsorbent. Okay, when you are using inorganic adsorbent, then you want to look into how it is formed, okay, how it can become this morphology. Let's say just now I share with you from this kind of morphology, right? The sea urchin morphology, right? So how can Fe, I think it's FeOH, how can this, okay, you start off with Fe 2 plus, I think 3 plus, Fe 3 plus. Okay, so from this Fe 3 plus, how it can react to form this structure. Okay? This is a morphology study, formation study. Okay, so by right, I can share with this kind of study. Usually we can do it by monitoring it at different time. Okay, let's say you are using hydrothermal approach. Okay, hydrothermal approach, and from Fe3 plus to become this structure, it takes you about 12 hours, right? Say you have 12 hours time. Okay, what you can do is that you can stop the reaction at different time interval. Let's say this is 0 hour. It's like this, right? It's ionic form, and then you stop it at 1 hour, 2 hour, 5 hour, and 8 hour. Okay, so you have various time interval, and at different time you take the sample. Okay, you take the product. Okay, let's say you react for 1 hour and then you take out the product. Okay, it's a powder, right? You can take that one. You can carry out characterization using XPS, maybe SEM, and XRD, right? So from here you can determine, like 1 hour maybe is like this. A nucleation starts to happen, and then after 2 hours you start to have a small structure, and then you have the osmotic ripening process. You will get very large structure, so you can track how it forms. This is an example of mechanism of formation study, okay, that you can look into, right? And then novel methods to prepare high performance adsorbent, okay, which means that you can look into what are the methods. Let's say the benchmark, the current capacity. Let's say the highest one that you can look at in the literature is like 1,000 ppm. Sorry, 1,000 milligram per gram, right? Okay, so if you prepare an adsorbent, the same adsorbent, let's say this is for AC, right? If you can prepare an AC activated carbon that can give you like 5,000 milligram per gram capacity, which means 5 times more than the currently used, okay, activated carbon, then this is something novel. One more is the revealing new insights. Okay, new insights to emerging instrument, which means that let's say you have new synchrotron or something like that. Okay, that one is a newly developed, something that is newly developed, and you take your activated carbon, you go and get data from that instrument, okay, and you can interpret it. So this will also let you publish quickly and easily, okay? Because things that people, the researcher or the reviewer don't know, they are less likely to question. When you have highly novel results, right? You are the expert in that particular area, and you send it out. When other reviewer look at the paper, sometimes they need some time to digest everything, and they will not be as good as what you are, right? So they will just accept the paper. Okay, so that's some strategies, okay. And another one is investigation using real wastewater. Okay. This one is quite lacking because everyone is using simulated wastewater, which means you prepare the wastewater yourself, okay, in the lab. Okay. You dissolve the salt and you use it. So whether it is usable in real wastewater or not, it remains to be known, right? So if the investigation is carried out in real wastewater, then the whole thing will be quite interesting for people to look at, okay? Because real wastewater, if you can prove that your adsorbent really works there, then you not also paper publication, you can also commercialize the product, okay? So there's some example that I want to share with you on this characterization. So this one, the boron nitride study that I have, just now I shared with you this one, whereby I look into copper and nickel adsorption, okay? And what we discover is that using XPS, we can deduce the mechanism, okay? Copper and nickel, they adsorb on the same active site. That's one thing. The second thing is that we confirm that the adsorption is through compactation and electrostatic attraction. Okay, all these two we confirm using the XPS technique. Okay. And okay, one more is this one. This guy. What is interesting and novel for him to publish in Journal of Hazardous Material is that he looked into the interactions between the adsorbent and the adsorbate using computational approach. Okay, so he can tell which site is the one that attached. You can see here, right? Which site is the one that attached to the biochar. Okay, you can see he draw this line and how they are formed and which one is the site that will bind with the adsorbent. Okay, you can calculate all this. Then you can also look at the electron density like this. All this through calculation. Okay, which means you have a computer and you can write some code, and then it will come out something like this. Okay, so he can even tell from the calculation about the bond strength and which one is stronger than which one and which one is more likely to happen. Okay. Yeah, this also the same thing from a different researcher. Okay, this one is published in Chemical Engineering Journal, and for this study, this researcher looked into interaction, and he even calculated the length between the adsorbate and the adsorbent, and he also looked at the adsorption energy, okay, using computational methods. So this in general is something that you will see more often in adsorption study, okay, especially in the CEJ, JHM, water research. All these are quite well-known environmental journal. So a lot of people are looking into incorporating computational approach into the work. Okay. Okay, so that's all for the adsorption part. Maybe I can take some questions. If you all have any question. Okay. Anyone? I want to. I will spend the last 10 minutes to address your question. Okay. So I want to go through the bioremediation technology, which is our topic today, right? And then at the end of this bioremediation technology, I want to share a bit on how we can develop a sequencing batch reactor. Okay, so a lab scale sequencing batch reactor can be easily developed for your study. Okay, so sequencing batch reactor is something that we use to culture microorganisms. So we'll look into that later in a while. So for this bioremediation technology, by the way, if you have any question, just write down in the chat section. Okay, so I can see that it's quite empty now. So if you have question related to this course, just write it there. Okay, I will answer it. Okay, so for bioremediation, the word bioremediation itself tells you that we are using biological process, okay, to carry out the removal of pollutant, okay, which means we are using microorganism, or maybe we are using enzyme, okay, to degrade certain pollutant. Okay, so I will quickly share with you some fundamentals and why this bioremediation works. Okay. So in wastewater, we usually have three types of oxygen demanding substances, and all these oxygen demanding substances they are going to consume the oxygen in your system. Okay, first one will be the immediate oxygen demanding substances, okay, which covers most of the time inorganic substances. For example, sulfide. Okay, so sulfide and Fe2+. Okay, so these two, they will react with oxygen. All the free oxygen that you have, they will consume it. But the good thing is that they are present in a very small amount in real wastewater. Okay, so that's why we don't see a lot of them in real wastewater. Okay. So this is first case, okay, immediate oxygen demanding substances. The second case that we have is the carbonaceous oxygen demand. Okay, which means that we have carbon compound, and the carbon compound can be used by microorganism to carry out metabolism and respiration. Okay, so when you have this kind of oxygen demanding substances, the second one, carbonaceous one, this means that oxygen is required by the microorganism. Okay, so when you have excessive amount of organic matter, then oxygen will be depleted by the bacteria. So another one is nitrogenous oxygen demand. So just to share with you, in wastewater, let's say we have domestic wastewater, right? Domestic wastewater is the one that we send to wastewater every day, okay, through our daily maintenance. Okay, we have to go to the bathroom, we have to take shower, we have to do a lot of things, right? Wash our hands and so on. So in the domestic wastewater, there are several things that you will see. Okay, one is the organic matter, right? Organic matter. The other one is the nitrogen. Okay, nitrogen, very commonly seen. And another one is the phosphorus. Okay, phosphorus also exists in the water. Okay, so for organic, the first one is the organic. You will have like microorganism consuming the organic substances and take up oxygen. Then we have the nitrogen. So the nitrogen itself will also consume oxygen. Okay, there's something called a nitrogenous oxygen demand, whereby let's say you have organic nitrogen. Okay, this one organic nitrogen is very common because this is protein, right? You know protein, right? Protein amino acids. Okay, amino acids which are the building blocks of our protein. The protein. Okay, we have different types of protein in our body. It's all the building blocks of our cell and so on. Okay, so this organic nitrogen, it will be broken down into ammonia. Okay? It's always like that. It's always follow this pathway. Okay, this is in general we call it as ammonium nitrogen. Okay, ammonium nitrogen means NH4. Okay, plus. And this NH4 plus, it will become nitrite and nitrate. So this is a nitrogen cycle, okay? A typical nitrogen cycle. Okay. Ammonia become nitrite and nitrate through nitrification process. Okay. And this when you form nitrate, right? Okay, from ammonia to nitrate, you are actually consuming oxygen. Okay, this 1 gram nitrogen, you need 4.6 gram oxygen. Okay, and nitrate, you can remove it from wastewater by denitrification process, which means it converts into N2. Okay. So I'll talk a bit on how we can achieve this in a while. Okay. So my subsequent slides will be on some introduction of bacteria, which I don't want to talk about because this one is more on the bio side, right? Biological studies, okay, on what type of bacteria that you have and so on. So you can go through this yourself. We have eukaryotic, prokaryotic, and so on, which means different things. Okay, so difference between the cells, they are all important, you know, because different microorganisms, they have different tolerance to a certain compound and so on. So they are all present in our activated starch. Okay, so I will skip all this. Okay, and in terms of classification, you can see that we classify them differently. Okay, based on many reasons. For example, what they eat and so on. Okay, and the size also important. Yeah, different things, they have different microorganisms, they have different size. Okay, okay, so in the activated starch, let's say you are using biological system. to remove your pollutant, your wastewater. There are several things that you need to know. The first thing is that in activated sludge system, it's always consists of mixed culture. Okay, mixed culture means that it's a huge diversity of microorganism. You have a huge ecosystem inside. Okay, that's the main thing that you have to know. And the second thing is that each of these different species, they behave differently. Okay, and for example, we have in the activated sludge, the microorganism that you have microorganism that can tolerate pH less than 5.5, okay, or what we call acidophile. We have some that can tolerate pH more than 8. Okay? You have some that can survive at 25 to 40 degrees and 50 to 60 degrees and so on. Okay? And you have aerobes, microaerophiles, and anaerobes, and facultative. Okay? You have all these different kind of microorganisms in active sludge. And the difference between the population is in terms of the number only. Okay? Whether this maybe you have an active sludge, the aerobes maybe is more than the anaerobes and so on. So the difference in terms of the quantity. Okay, this is very useful because let's say you have a wastewater. Okay, first week. Okay, first week you have wastewater that you introduce into the wastewater treatment plant pH 5. Right. So the first week you introduce pH 5. In the active sludge, all the sludge that you have, right? Some will not be able to tolerate pH 5. Some can tolerate pH 5. Okay, so all the ones that can tolerate pH 5 will start to grow excessively. Okay, that means you have a lot pH 5, and just a bit of the one that cannot tolerate maybe pH more than 5. Right. Let's say in the second week, suddenly the wastewater that you have no longer pH 5. Okay, it becomes pH 8. Okay. So you introduce this water into the wastewater treatment plant. All the pH 5 at that point of time will start to die. Okay, the population will start to be lower. Okay, and the one that can tolerate more than 5, maybe they can tolerate more than 8. Right, it will start to grow. Right, pH 8. Okay. So this kind of properties is what we call the resilience, the tolerance of the plant. Okay, this is related to that. And if you have a mixed culture, you are able to tolerate environmental change better than compared to when you have a single culture system. Okay, that's why you can see all the wastewater treatment plant, you always have a mixed culture system, which means you have an entire different species of microorganism instead of just one or two. Okay, so we have a diverse type of microorganism. I will skip this. We also classify them based on different food that they take, like light, CO2, sunlight, and so on. Okay, look at this table. Some use light, some use inorganic substances, and so on. So we call them differently. Okay. So what I want to talk about now is in terms of the type of electron acceptor, okay, that the microorganism take, okay, so that they can use it to metabolize their food. Okay, they are in this wastewater. We have quite a number of oxidizing agent, okay, or electron acceptor, okay? And the most preferred one would be the oxygen. Okay? That's why we have to supply oxygen into the wastewater treatment plant, because the reason is because oxygen itself, okay, will give you a lot of energy. Okay, that's why bacteria like it. They do a very low amount of work, but they can get a lot of energy. 686 for this case. Okay, okay, for a different kind of electron acceptor, for example, nitrate. Okay, nitrate itself gives you slightly lower compared to oxygen. Okay, 649. Sulfate 190, and the last one, methanogenesis. Okay, it gives you 8.3 only. So first one, oxygen, is when you have aerobic condition. Okay, when you have aerobic condition, you will have the bacteria taking up oxygen and use it to build ATP. Okay, ATP means that you are using it to for respiration and so on. After that, once all the oxygen has been depleted, then the next source of energy, electron acceptor, that the microorganism will take up is the nitrate. Okay, nitrate reduction or denitrification can only happen under anoxic condition, which means no oxygen. Okay, low oxygen condition. Once nitrate has been used up, then only sulfate. Okay, we look at sulfate. And finally, once sulfate has been used up, we have the methanogenesis, which means that your organic substances starts to degrade into methane gas. Okay, this is methane. Okay, and you can see it only releases 8.3. Okay, energy, relatively lower compared to when you have oxygen. Okay? And most of the energy is still stored in this one, CH4. Okay, that's why it's good to some people feel that it's good to store it as a CH4 because CH4 you can separate it easily from the water, and you can use it as energy to do many things. Okay, so it depends on the type of application that you want to look at. Okay, aerobic respiration in wastewater treatment plant, it consumes the most energy. Okay, that's why it's not so good nowadays when you want to inject energy into the wastewater treatment plant, and then you waste a lot of energy, and it's not so good for the environment. Okay, just to share with you, yeah, this is how the bacteria in activated sludge grow. It always start with lag phase. Okay, and then lag phase is when you need to adjust, okay? Adjust to the condition, the situation, the wastewater that you have. Okay, you introduce the wastewater into wastewater treatment plant, and then you always have a lag phase first. Okay, depending on the toxicity of the substance. Okay. If you have very toxic wastewater, the lag phase will be longer. Okay. If you have, let's say, phenol, then you can take up to many days before you can see degradation starts to happen. Okay. This lag phase means that the bacteria needs to adjust itself, okay, to make sure that they can survive. They are tolerant to the condition. The one that cannot tolerate, it will die off. Okay? So the one that can tolerate, it will start to build and grow excessively until the food consumption is almost like equals to the growth rate. Okay, so when this happens, then we have stationary phase, okay? Which means the food is just enough, okay, for the population to eat. And suddenly, once the food starts to deplete, then we have the death phase. So most of the time, this is how it happens. So for us human, we also go through this kind of curve. Okay? 100 to 200 years ago, we are probably at the lag phase. Okay? Now we are at the log phase. Okay? Human population is in log phase, and I think we probably is somewhere around here. Okay, we are at around 9 billion, right? 9 billion people. Okay? So if you look at the projection, we can actually go up to 10 billion, okay, around 10 billion, 10 to 12 billion, and then we will reach a stationary phase, and then hopefully we will not reach the death phase. This is preventable if we innovate something that can solve our food issue, or maybe we can colonize somewhere else, like Mars, right? If you look at the recent news, Elon Musk said that we are going to colonize Mars in 2050. Okay, we are going to nuke Mars to make it habitable. So we don't know what will happen, but let's see how it goes. Okay, so many types of bacteria, aerobic, obligate, and facultative, using different type of electron acceptor. Okay, so I will we'll skip all this. Okay, so this is what I said just now. Okay, the most important electron acceptor is the oxygen. Okay, oxygen is the one that we can have high consumption. Okay, initial high consumption, because this one gives you the most energy. Okay, and then after this you have the nitrate, right? And finally you have the sulfate. Okay, once the nitrate starts to deplete, you have the sulfate. Okay, sulfate starts to be used up. Okay, so I want to explain a bit on how we can look at this this graph. Okay, because this is what happened in wastewater treatment plant. Okay, so initially you have an introduction of wastewater into the system, right? You introduce it, and then you will start to see that you introduce it as BOD. You start to see BOD decrease, right? As BOD decrease, you will also have the dissolved oxygen decrease. So why DO decrease is because the oxygen is used to degrade organic matter in the BOD. Okay. So the next one would be the organic nitrogen. So when you have the organic nitrogen introduced inside into the wastewater treatment plant, if you have protein, let's say protein, it will start to be degraded to become this one, ammonical nitrogen. Right? You can see that there's a sudden rise because organic nitrogen converted to inorganic nitrogen, and then you start to see a decrease, okay, along with the increase in nitrite. Okay, so nitrite will increase to a point where it will be converted to nitrate, right? Nitrate will start to increase. So typically it undergoes this kind of conversion. Organic nitrogen, it goes to nitrate. Okay, so if you look at the wastewater treatment plant, it's not good enough to convert organic nitrogen to become nitrate. Okay, so organic nitrogen, when you add in, let's say you have the feed. Okay, your feed is contains organic nitrogen, right? It goes to wastewater treatment plant, and the first step that it operates is the aerobic step. Okay, it's always aerobic step. Okay, which means you introduce oxygen through using a diffuser. Okay? You have a lot of diffuser here. All these diffuser, they will bubble up a lot of bubble. Okay? Your organic nitrogen will be converted to nitrate. Okay, it will be converted to nitrate through this pathway, and then after that, your nitrate, you cannot just release it. You have to undergo another step. Okay? This is the anoxic step. Okay? And all the nitrate will go into the anoxic reactor. Okay? These two, aerobic and anoxic, they can be of the same reactor. Okay, they can be one reactor, which is operated with aerobic and anoxic stages. Okay, so this NO3 will be going to anoxic stage, so that NO3 can be converted to N2, okay, through the denitrification process. But to convert this nitrate into N2, you have to have a carbon source, okay, which means that you have to have something with carbon so that you can have this kind of reaction to happen. So if you look at the earlier equation, okay, nitrate reduction equation, you need carbon. Okay, this is the carbon that you need. Okay, so that you will get CO2 plus. I think there's some error here. It's supposed to be N2. Okay, nitrogen. Yeah. Yeah. Sorry. This one. Is this one. Okay. Denitrification. So you have this one, right? You need to have a carbon source to convert it into nitrogen gas. So in a real wastewater treatment plant, to achieve this carbon source requirement, some operator they add in ethanol. Okay, they add in ethanol into the anoxic stage so that they can have the carbon source for the denitrification process to happen. And this is one strategy. The other strategy is they don't treat this aerobic stage fully. Okay, they sometimes they can optimize it to such extent whereby you still have certain carbon here, and then you transport it into the anoxic tank, and this carbon source can be used to carry out the nitrification process. Okay, there are many ways to do this kind of denitrification. Okay? But the important thing is that a carbon source is needed. Okay, so I asked several wastewater treatment plant operator, and they some of them said they use ethanol. Okay, and besides ethanol, I can't remember whether methanol was used or not, but I don't think so. I think it's ethanol only. Okay, so that's crucial for the nitrification to be happening. Okay, so the third graph talks about the growth of bacteria. Like just now, what I said, same thing. Bacteria will grow excessively when you are food, and then they will die. Okay? When they die, the algae will start to grow. Okay? Algae is a microorganism that takes CO2, okay, as their carbon source. They only need nitrogen and phosphorus in the water. Okay, that's why they can grow rapidly after the death of bacteria. Okay? When bacteria die and you have nitrogen and phosphorus in your water, okay, if you walk around, if you have a lake nearby, you look at the lake. If it's greenish in color, you probably know that you have a lot of this algae. Okay, and you know that your lake is polluted with nitrogen and phosphorus. Okay? Because these two, they are the driving factor that will affect the growth of this algae. Okay. Okay, that's all for the some fundamentals on why we use microorganism and what are the things that microorganism can degrade. So we want to look at the secondary treatment. Okay, secondary treatment means that usually is biological process. So in a modern wastewater treatment plant, okay, what we will see is that the wastewater will go to preliminary treatment. So these two, they are often termed as the preliminary treatment, okay, to remove all the solids, okay, the large solids. Sometimes people throw tissue papers, some people throw underwears or anything into the wastewater, right? So all this will end up here. Okay? It will be here, and it will be filtered to the primary treatment. Okay, so I went to some wastewater treatment plant. Okay, and I asked them what's the worst thing that you can find in this primary treatment, the solids. Then what's the worst thing that you can find? And they told me that yeah, some people throw babies, babies into that this into the wastewater. That's quite sad lah, to say lah, right? So that's the worst thing that they can find there. Okay. And anyway, this primary treatment will filter everything, all the solids, right? And this water that comes out from primary treatment is what we call the primary effluent. And primary effluent goes to the secondary treatment. And this one biological process. After that, it goes to the tertiary treatment, okay, which can be disinfection and so on. Okay, so this is how it looks like. Primary treatment, you have bar screen, grid chamber, and clarifier. Okay, setting tank is also called a primary clarifier. Okay, so primary clarifier to remove all the excessive sludge that you will find. Grid chamber and bar screen, they are used to filter off larger things. Okay, so after that, it goes to a tank, the secondary treatment. Okay, biological process. And from here, you can have aerobic stage, anaerobic stage, aerobic or anaerobic mixed together, and so on. Then they will go into the excess sludge will go to the sludge digester. Okay, there will always be excess sludge, okay? Because microorganism will consume your wastewater, okay, which contains a lot of carbon, and it will turn it into food for them to grow. So they will grow excessively and they will become carbon, okay, all this sludge. And all this sludge is not like a 1 kg or 2 kg. Okay, it is quite huge. The amount is a lot and it's generated every day. Okay, so when I visited one of the wastewater treatment plant in Penang, okay, in the Batu Fringgit area, okay, it's nearby at the center of the Penang Island, right? So I went there and I asked them about the sludge. What I discovered is that the sludge that they have, right? They send it to landfill. Okay, the excess sludge that they generate every day, they send it to landfill, and it's not a sustainable process. So so this is something that we want to avoid. Okay, to send the sludge to landfill, because we generate the sludge every single day. Okay? And the sludge itself is like, when you use it for landfilling, you put it in the landfill, you are actually wasting the space in the landfill. Okay, so landfill is an engineered system used for solid waste management. Okay, so if you throw the sludge there, then eventually you will saturate the landfill, and the landfill will need to stop operating because there's no more space for the sludge. So I would say that for the sludge, the best way to treat it is to look into ways where we can use it. Okay, for example, landfill, you can use it to recover some energy through incineration. Okay, incinerate the sludge, but of course, incineration sludge also, there are several drawbacks. Okay, like you have to deal with the bottom ash. Sometimes you have dioxin pollution and so on. So that one will be some other topics. Okay. So for secondary treatment, we use it for biological degradation of pollutant, okay, pathogen removal to a certain extent. And the common one, okay, the common one include aeration, okay, or activated sludge process. We have the trickling filter and lagoon, okay, oxidation pond. So just to quickly go through, second treatment, that means your activated sludge, okay. So all these are the sludge that you have. And you can see this, all this is the wastewater, okay. And you have a lot of bacteria here. If it's empty, you can see a lot of different dots here. All these, they are the diffuser, okay, whereby water will come up, bubble will come up, okay, bubble will come out here. You see a lot of bubble, right? All these bubble, they are the oxygen for the microorganism. Okay. So one more is a trickling filter. Trickling filter is another way of treating secondary effluent. This is not really widely used nowadays because of many drawbacks. One thing is that this one, you have something like this, okay, some very long thing here with a lot of point, so that the water can be spread into the media. So the media will consume this wastewater, okay, the substances in the wastewater. So we are flowing through the porous media, and the porous media contains biofilm. Okay. So the reason why this is not really widely considered nowadays, because there are many problems. For example, clogging. Okay. So sometimes you have clogging issues. Sometimes you have methane gas issues. We expect that this upper part will be aerobic zone and the lower part will be the anoxic zone. But sometimes it can turn into anaerobic zone, okay, whereby a lot of methane gas being released. So it's very polluted, and it's like less easy to control compared to the activated sludge process. Okay. So one more is the oxidation pond. Okay, oxidation pond, we use it. Okay, for this one, there are many types. You use it for low cost wastewater treatment, but you need a large land. Okay, we generally this process of transporting the water into this large space, okay, and then wait for it to degrade by itself. Okay, so something that I don't think is better compared to the activated sludge. It's the least effective one. Okay. Okay, so once you generate the sludge, you have to treat it, and many ways to treat it, including dewatering, and then you can send it for aerobic digestion or anaerobic digestion. Okay, so for treatment goal is to reduce the smell, reduce water volume, and try to decompose some of the organic matter. Okay, so aerobic digestion, okay, we also have this, but it costs a lot of energy, and although it's faster, it consumes a lot of energy, which is not so practical. Okay. Another one is anaerobic digestion. This is very widely used, yeah, because you can generate energy from it. Okay. And you can see every time you go to the nearby wastewater treatment plant, you can see this kind of structure. Okay, this shape. Okay. This is the anaerobic digester. Okay. Sometimes it's like this, a large shape like this. Okay. But once you look at this kind of building, right, you directly know that this is the anaerobic digester. Okay, and you use it to recover certain biogas like methane, carbon dioxide, and so on. Okay. After treatment, you can use it for composting. You can do composting, okay, to get the compost, and the compost you can use it for planting plants, because your compost is full of nutrients for your plant. But if you ask me, my personal view, whether I will want to consume this kind of plants, okay, I would say no, because there are many factors that affects my choice. One thing is that if you are using sludge for composting, there could be heavy metals, okay? And heavy metals can be taken up and bioaccumulated by your plants. Okay, a lot of problem if you use it. One is acceptance, one is heavy metals, and the other one is there could be some pollutants, okay, like micropollutants and so on. So the sludge, they can absorb this pollutant, and after you treat it, right, pollutant is still there. Okay, most probably it's still there, okay, depending on the way you treat it. And if you use it for composting, of course, it will be taken up by the plant. Okay, so if you eat it, then all those heavy metals will be in your body. So I will avoid this kind of agricultural product. Okay, so it's just my personal view. Then disposal, like I said just now, sludge also sometimes there are operators disposing it in the landfill. Long time ago, it is a common practice. Okay, and today, no, you cannot do that. Okay, but some still practice this kind of approach, landfilling, which I won't really recommend this approach. Okay, if you are going to be a landfill operator, make sure that you don't accept any sludge, because sludge, first thing is that if they give you sludge with a lot of carbon, if you put it in the landfill, then you will start to have a lot of methane coming out, right, and so on. So there are a lot of problems. Okay? And the sludge itself will take up a lot of space because it's generated every day. Okay, so that's why we want to prevent sludge from coming into the landfill. The second one is incineration. Okay? Incineration process it gives you heat and energy, but not a lot. Okay? Incineration of sludge not give you excessive energy. Okay? Incineration means that you burn it to recover some energy. Okay? Sludge is not a very good energy source. Okay? Not a good feedstock. Okay? Compared to like coal, okay, or maybe biomass. Okay? Coal, the heating value is very low. Okay? The energy given by sludge is quite low, okay, compared to others. And sludge tend to give you more pollution, okay, compared to biomass and coal. Okay? So that's why sludge more difficult to handle, more problem. Okay? That's why you can see some countries they want to carry out such incineration. So what they did was they blend sludge with some other feedstock. Okay, they mix together and then they incinerate it, okay, to get the energy. Okay? This approach can also reduce the volume of sludge that you need. Okay, so just to quickly go through just now the stabilization bonds that I talked about. We have three types. This is a lagoon. Okay, we have anaerobic bonds, facultative, and maturation, all with different properties. Okay, anaerobic bond is using anaerobic process. Okay, which means that you have a land and then you have the wastewater flowing in. Usually, you have a scum layer at the top. This scum layer, most of the time, is oil, okay, or fatty acids or so on. Okay, it will form something above. It's all fats, okay. And you have a oxygen lacking condition at the bottom part, okay, whereby you have methane gas being generated by the sludge. Okay, and I'm not sure whether some people will recover the methane or not, but of course it can be recovered. I'm not aware of where this is conducted. Okay, I mean, I'm not aware where people recover methane from. Okay? Whether there's any anaerobic pond whereby there's a setup to recover the methane. But when you want to recover methane from wastewater, right? Let's say you have a high strength wastewater. Okay, you have this treatment, anaerobic treatment. Okay? Then you will release. You want to recover methane gas. It's not so easy sometimes because the methane gas that you get sometimes comes with the H2S. Okay, so H2S, and sometimes you have CO2 also. Okay? So this H2S itself is a corrosive gas. When you want to use this methane to power something, maybe like a wind turbine or something like that, you have to remove this H2S first, okay, before you can use the methane gas. Otherwise, you have corrosion. Okay? Corrosion is quite bad, okay, if you have H2S. Okay? Because sulfur compound they can attack the metals that you have. So sometimes when you want to recover it, they will use a specialized tubing coated with certain things that will prevent prevent corrosion effect. Okay. Then the facultative pond, another one treatment lagoon, okay, one treatment system. This one more on using aerobic and also some anaerobic layer, two different layers lah. Okay, they are operated together lah. You have anaerobic and then facultative. Sometimes facultative can be done the first one. There's a sequel. Yeah, something like this lah. Wastewater, it goes to anaerobic first, then facultative, and then maturation, and you can have more. Okay. The final one is the maturation. Maturation is when you use it to do disinfection. Okay. Design criteria is depends on the quality of water that you want. If it's the downstream application, if it's for, let's say, if it's for unrestricted irrigation, then you can develop it to a lower size. Okay, the size of the maturation pond is determined by the wastewater, the water, okay, that you want to use it for. Okay. Okay, so let's see if you have any questions. Still no questions from everyone. So let me just go through this aerobic and anaerobic granules. Okay, so this is one of the innovation that I want to bring to your attention. This is aerobic granules, okay, or anaerobic granules, whereby there are researchers who found that the sludge, okay, the microorganism, can be tuned to form granule-like bits. Okay, so this is all granule-like bits. You can see it's like this. Okay, and this granule-like bits is very critical because all these bits, they improve the overall stability of the system. But there are many disadvantages. For example, if you want to develop these bits, it takes a long time. So I also have some experience trying to develop these bits for phenol degradation, but it doesn't work. Okay, I tried, but unfortunately it didn't work. And the reason is because to get this kind of bits, you have to have long startup time. Second thing is that not all sludge can be used to form bits. Okay? So some of the bacteria, for example, for my case, I use it for phenol, and phenol usually is filamentous. Okay? The microorganism that can be used to remove phenol is filamentous in nature, okay? And it has certain properties that make it difficult to form bits. Okay, probably it takes longer time than the normal time that's needed. So I did not continue to develop the bits because of various challenges. Okay, so but the bits itself, the granules itself, is very useful. Okay, in fact, large scale application has been proven to be effective. Okay. One example, one paper that I want to share with you is in terms of the application of these aerobic granules in membrane bioreactor. Okay, so this paper published very recently talk about how aerobic granule can be used to reduce the fouling of the membrane in membrane bioreactor. So what this study did was they looked into the confocal laser scanning microscopy. And here you can see the difference. R2 is aerobic granule, R1 is activated sludge. So for R2, the color is less intense. Reason is because less attachment of microorganism to form biofilm. Okay. So one more is immobilized biomass. Another innovation. One of my colleagues is working on this immobilized biomass, which means that you are using polymers to trap the biomass in the polymer and then use it for your application. There are many advantages and disadvantages of this process, but just to share with you, yeah, this one you can use PVA or maybe sodium alginate, okay, to do this kind of bits. Disadvantages is that you tend to have a reduction of the bit volume over time, And sometimes the biomass can escape from the peaks and form the activated starch. So it's very difficult to control. Okay? If you immobilize microorganism, but if you immobilize an enzyme, that will be easier. Okay? So before I end today's lecture, I just want to show you how we can actually build a sequencing batch reactor. And this sequencing batch reactor can be used to study a lot of things, right? For example, you want to culture the bacteria to treat phenol. You can do that. You want to culture the bacteria to treat, let's say, heavy metals. You want to study how the heavy metals will influence the activated starch process. You can also do that. You can also design this system so that you can get aerobic granules. So how we do it? This is I would say a low cost way of doing. Okay, this is a simple setup whereby you only need several things. One is the timer, right? Then one is the pump. Okay. Then you have to have a beaker or any container to put the feed. And this one is the reactor itself. And then you have the tubing. Okay, you need to have a tubing. One tube is for draw, one tube is for fill. Okay, so what happens is that you will operate it. Okay, after you have set up something like this, okay, you will operate it through this cycle: fill, react, settle, draw, and idle. Okay, these 5 cycles. When you have fill, that means that this part here, you fill up with a feed. Okay, any feed. Then during the fill time, let's say you have 1 hour fill time. Then this pump here will draw all the feed slowly into the reactor. Okay, after everything has been drawn inside, right? Then you have the react phase. Okay, react phase, the second one. Maybe react phase, you can put it at 8 hour. Okay? And in the react phase, you can have, if you have 8 hours, you have 4 hours aeration. Okay, you can have a air pump. You can buy it from the aquarium, right? The aquarium, you have this air pump whereby you can have a lot of bubbles, right? So 4 hours aeration and 4 hours of only stirring. Okay, to stir the reactor, you can buy something called an ejector. Okay, this one you can also purchase from the aquarium. Okay, they call it as ejector. Okay, so you can stir it without aeration. Okay, so after the react phase, you can have the settle phase, whereby there's no aeration, there's no agitation. Okay, which means you don't touch the reactor. You let the, let's say this is a reactor, you let all the microorganisms settle down. Okay, so it will be here. All this here is settled down. Let's say this is, you have a 10 liter, right? Then maybe this is 3 liter, right? It settles down below this 3 liter, and after settle down, maybe you give it 1 hour, and then after you have another draw phase. Draw phase means that you have this tubing that's here, around here, or maybe around 3 liter. You draw out the solution above the settled sludge. Okay, maybe 2 hours, right? Then after you draw out, then you have the idle phase, whereby your reactor is resting. Okay, so you have 12 hours of for this and 12 hours of rest phase. And then the next day, the fill phase start again, and then it goes through the same cycle again. So this way you can use it to culture your microorganism or your activated starch for any study. Okay, maybe you want to plan to use it for investigating how you can immobilize it on the polymer. You can culture the bacteria to do it this way. Okay, so that's what I want to share with you. Something that's more practical. That, you know, if you have interest, you can look into operating this. So this is operated under aerobic and anoxic stage. If you want to do it in anaerobic, you have to seal everything tightly and so on. Okay, if you want to make it even better, you can put in some sensors, pH sensors into the reactor, so that you can monitor online what is the pH and so on. Okay, so this is a 24-hour cycle. You can do it 12-hour cycle or 4-hour cycle. So to culture this and stabilize for 24-hour cycle, you probably need about 3 months. For 4 hours, maybe you need 1 month. Okay? But the 4 hours is more tedious because you have to prepare the feed every 4 hours. Okay? 4 hours, once you draw, you fill the tank, then you have to prepare again and again. Okay, so there are a lot of opportunities to use this biomass for many studies. Okay, in fact, even preparation of adsorbent, you can even use biomass like this starch. You can also do it. Okay, so I think I will end this today and take in some questions. Okay, so thank you so much for your time yeah. So in case you have any question, because I didn't see any question here, right? So I continue. Yeah. So
Yeah.
Okay.
Thank you so much, Dr. Wenda. Very, how to say, very fruitful lecture, I guess. So many lecture content as well as the new innovation, yeah, that you've been developed in your laboratory. So for some, how to say, innovation in terms of adsorption or adsorbent characterization, I guess for our student is quite the new knowledge, especially for advanced characterizations.
Okay.
Yeah, that's why maybe how to say no question. Yeah, it could be clear or yeah, very new information for our student.
Okay.
But yeah, anyhow, it would be a great how to say information and also motivation for them to learn more. For example, like Raman spectra. Yeah, I guess
Yes.
in our material characterization, the topic hasn't yet delivered. Yeah. So the difference between Raman spectroscopy and FTIR spectroscopy, I'm not sure if all students already have that information. So quite new. But anyhow, that's good, I guess, yeah, to motivate them to learn more about that. And today, I guess the content of the lectures very, how to say, very comprehensive. Not only about the innovations in adsorption study, but also how to say the many advanced characterization method, or technique of adsorbent have been introduced by Dr. Wenda. And the good thing as well, Dr. Wenda, is you also share with us about the some strategies, to investigate the adsorption of pollutants.
Yes.
Yeah, it would be great idea for our student, especially for designing the final project.
Okay.
Because all students who join with this class, already how to say, focus with the environmental chemistry issue. Yeah, they can work with the how to say, treatment of the pollutant, or even though one of the students actually who attend this lecture also already concerned with the computational modeling. So maybe later on, they,
Okay.
she can apply that kind of idea. But anyhow, very good to give the great overview to students what kind of the topic, that's still very promising for publications in terms of environmental chemistry or designing material for environmental applications. And the other thing about the bioremediations, actually they have been learned in the previous lecture, but very general. So in this way, very thankful you can deliver in other way, very fundamental, I guess. How, for example, the oxygen demands processes, 3 processes that you mentioned, you also deliver is also good. So it can be complement, for student informations regarding to the bioremediation. Yeah. So, dear students, if you have any questions or inquiry to Dr. Wenda, please kindly raise your question. You can also deliver in Bahasa. Hello? So silent. Silent could be yes or could be, could be they still, how to say,
Need some time to digest. Right?
Yeah. But anyhow, many advanced characterization in our study program, mostly how to say, study in the magister program, especially for XPS, something like that. So for undergraduate, it's quite the new information, I guess. But anyhow, no problem. It would be great for them, as the early information.
Oh, they will study that. They will study those. Okay.
Yeah. Any other information, Dr. Wenda, for next week meeting?
Okay, next week I will cover about disinfection, disinfection technology. And yeah, so what I have is I hope the student can complete the assignment that I have, right? So that they can submit next week. So that's one thing, submission of your assignment. Then this week's assignment also in form of questions. If you have any problem answering the questions, you can get back to me. I will help as much as I can. Then next week, course, we will look into some of the disinfection technologies and what has been done so far. So I can talk about actually disinfection. There are quite a number of different things that we do. Okay, for example, in water, we look into chlorination as one of the most common one. So in innovation, we also have some researcher designing materials that can be used to disinfect various waters. So we will talk about that next week. Okay.
All right. And for assignment, it's been posted in your how to say link?
It's already I already posted last week.
Okay. So all right. Yeah. So to all students, just to remind you, so please kindly fulfill the assignment that been determined by Dr. Wenda, and the due date must be next week, right? For submission, the assignment.
Yes. For last week's assignment is next week.
Okay, and the due date is next week, so please keep the due date, and yeah, good luck. If you still have any question for completing your assignment, please kindly, how to say, and feel free to contact Dr. Wenda or me, myself, if you have, if you need any assistance to complete it. Okay, I guess that's all for our meeting today. Thank you so much, Dr. Wenda, for always, how to say, inspiring us, for many new informations. And for me, myself, then I knew what kind of the new content that can be, how to say, added into our lecture content, for the futures. Thank you so much. And since the time is over, so we would close this lecture for today. And again, thank you so much. Wish you all a great health and also a great day. Thank you so much, Dr. Wenda.
Thank you.
Yeah, and thank you for everyone, and see you again next week. Okay, and don't forget to complete your attendance list, attendance link through the link that been provided in the chat room. So please kindly fill it. Okay. I would close this meeting since also I have to move to campus for the activity. Bye. Thank you so much, Dr. Wenda. Wish you a great day.
Thank you.
Okay. Okay. Thank you, everyone. Thank you, everyone. Okay.